Hello and welcome to another video in the CERG Showcase series. I'm delighted to introduce Dr. Nimesh Mistry for this video presentation. And Nimesh is a Senior Teaching Fellow in the School of Chemistry at the University of Leeds. Nimesh obtained an MChem in Medicinal Chemistry at the University of Leeds in 2006, followed by his doctorate at the University of York, which was completed in 2010. Nimesh remained in York as a teaching fellow in the Department of Chemistry, and in 2013 he moved back to the University of Leeds to take up his current position. Nimesh's interests are in the development of innovative approaches to enhance student education using the scholarship of pedagogic research. His natural focus is applying this to chemistry education, but Nimesh is moving towards approaches that can translate across disciplines. So for this video presentation, Nimesh will present on identifying misconceptions and threshold concepts in organic chemistry.
Okay, so I'd like to thank Suzanne and Michael for inviting me to give this CERG webinar. What I thought I'd do is just start off by giving a short intro into how I got into chemical education research and what areas that I'm interested in before talking a bit about some work that we're doing trying to identify sort of misconceptions and threshold concepts in organic chemistry. So I started getting interested in CER from my very first sort of teaching experiences, and that's because it became very apparent that the students that I was teaching weren't necessarily approaching their studies, such as tutorials or lab work, in the same way in which I did as a student. And so I sort of very quickly sort of realised that I can't sort of use my own experience as sort of the model upon which to base my teaching practice. I need to get a good understanding of what it's like for most students going through whatever sort of teaching sort of scenario. And so it's from there that I started becoming interested with educational research. And these are sort of the various different ways in which I've tried to become engaged with educational research. So I think my first sort of experience of educational research was actually through my teacher training courses that we have sort of at the university level, where I sort of achieved sort of HEA accreditation. And this introduced me to the scholarship of teaching and learning and how to use sort of the literature to provide the evidence and the foundation upon which to design your sort of teaching practice. And so from there, started sort of engaging with the literature and the literature that's out there. So things like CERP and Journal of Chemical Education are journals that I regularly read. And then also attending conferences like VICEFEP or non-discipline specific student education conferences as well, just to get an idea of sort of the evidence that's out there and sort of methods that I could use to evaluate my own practice as well. And then finally, I guess what's also been really important is to connect with people and use networks to meet sort of like-minded people. So Twitter has been great for that. And also, I think we're lucky in Leeds that we've got some really great educational organisations as well. So things like the Leeds Institute for Teaching Excellence, LIGHT, and also PRISM as well for those in pedagogic research in the sort of sciences and maths. And so in terms of the type of educational research that I'm interested in, I should firstly point out that I'm not necessarily just interested in doing educational research for the sake of it. It's always linked within sort of trying to apply it through sort of teaching practice, either directly through what I teach or through sort of course improvements as well. And so what we use pedagogic research for is to sort of provide the foundation of the methods that we use, and then also the evaluation of any sort of teaching enhancement that we do. So I'd say that the two things are kind of blended together, and the ways in which we apply this are two sort of areas of teaching that I'm involved with. So we've done a lot of work with sort of improving our laboratory course. I'm also involved in outreach and widening participation, and being sort of an organic chemistry-focused teaching fellow, sort of organic chemistry educational research as well. And it's in this area that I'd like to talk about today, and give a snapshot of one of our first projects that we've been involved with in organic chemistry education. And whilst there have been some useful sort of studies out there, a lot of the context of the research and literature in organic chemistry education has been within a North American or European sort of context. And really in UK chemistry education, a lot of our students actually learn or introduced to organic chemistry just before in their sort of schools, before they actually come to university. And so what I wanted to do is kind of get a UK perspective on what difficulties students have with sort of fundamental mechanisms that we sort of teach and cover in our first year, and those fundamental concepts as well. And so the research questions around this project are around about how do students sort of apply their knowledge of the fundamental mechanisms, and what concepts do they use and apply. And from there, can we uncover some sort of misconceptions and threshold concepts that they may have. And so I'll talk a bit about threshold concepts in a bit more detail, but this was an idea that was first sort of developed by Mayer and Land about 15 years ago, talking about certain concepts which students seem to find difficult, but are sort of hurdles that they need to get over to get a greater understanding of the subject. And so at the very beginning of their paper, they really describe what a threshold concept is quite well in a couple of sentences. So this is the first opening paragraph, which describes a threshold concept as being considered akin to a portal, opening up new and previously inaccessible ways about thinking about something. But once students have grasped that sort of threshold concept, it can transform their way of understanding, and they need to sort of do this, because without this, the learner cannot progress. So we developed our own sort of methodology to identify how students were using and applying their knowledge of fundamental organic chemistry reactions. And so we designed a diagnostic test with 6 questions covering the main sort of fundamental mechanisms that we teach in the first year, and their underpinning concepts as well. And so these were all sort of questions that required sort of mechanistic problem solving and a free text response. And so what we did is we sort of would go to certain sort of lectures. So in particular, we focused on sort of second year lectures where students had just sort of learned their first year mechanisms, and to see what they can remember from their first years. We would go into a particular lecture, and then we would randomly distribute one of those 6 questions to each individual student, ask them to complete the question, which usually take about 10 minutes to complete, and then we collect our data as well. And we'd also pick courses where we could actually give this feedback back to the students, where it would be beneficial to the courses that they're learning as well. And so we went into sort of second year retrosynthesis courses where students would be applying a lot of this material as well. So that would encourage their participation to answer these questions. And so what we've been doing is we've been gathering data mostly from lead students so far. And so by doing this, we've been able to sort of get sampling from between sort of 60 and 80% of our cohorts. And we've also started looking at seeing national, trying to get our understanding on a national perspective. So we've gathered some data from Warwick so far, but we are also interested in getting some further sampling from other UK chemistry departments as well. But so far we've managed to get a good amount of responses for our diagnostic tests, and per item we're looking between 30 and 50 responses that we're analysing and interpreting. But again, we're interested in building up that database as time progresses. So one of the things we did with our methodology is we developed our own method of analysing and to identify these misconceptions and threshold concepts. And so the first part of our analysis was to use quantitative methods. And what we did is we broke down each question into various codes, where a code would be correspond to an aspect of the mechanism or the underlying concepts that the students could apply to answer those mechanisms. And what we did is we scored whether or not the students were correctly or incorrectly using each particular code. So green represents if they're using the code correctly and they were given a score of +1 for that particular code. Red represents if they're using the code incorrectly and we'd give them a score of -1. And we'd also leave it blank if students weren't engaging with that particular code. And what this allowed us to do was to then, once we'd scored the students and ranked them together, we could see quite clearly sort of clusters of students' responses. So we could see that students' responses weren't random; they were organised together by particular types of responses. So this helped us confirm through our analysis that students have sort of particular levels of understanding of organic chemistry and the underlying sort of concepts. And then what we also sort of further verified this is when we sort of did our next stage of analysis. So we sort of analysed each cluster using qualitative methods. We could see that within each cluster, students were given pretty much the same sort of responses and the same types of reasoning as well. Again, showing that there are certain levels of understanding. And what we could basically do using our clustering approach is sort of identify responses as being sort of fully correct, sort of partially correct, or sort of incorrect as well. And what I'm going to do is just highlight one of the analysis in a bit more detail of one of the questions from our diagnostic tests, but certainly the findings that we generated, as I'm going to show with this one particular question, was sort of also seen across all the questions that we analysed as well. So in this particular question, what we wanted to do is ascertain whether or not students had a good understanding of how the carbonyl functional group reacts with nucleophiles, but also if they had a good understanding of the structural differences between functional groups like ketones, for example, and esters as well. So what happens in this particular question is sodium borohydride reacts as a nucleophile, but it preferentially does so as the ketone is more reactive. And what we found through our sort of quantitative analysis is that we could cluster the responses into correct responses, of which we had 33%, partially correct responses of 41%, and incorrect responses of 27%. And we saw no sort of cohort effects or institutional effects either. And so students from each of the years, from Leeds and from Warwick, were nicely organised within these clusters. So if I start with what we saw with correct students first, what we saw is that correct students correctly understood the reactivity of the carbonyl group, so that it reacts with nucleophiles carbon, and borohydride reacts as a nucleophile, and then also the ketone was the carbonyl group which reacts in this particular reaction. And so we think about the concepts that the students are applying. Essentially, through all our analysis, the main sort of difference between the concepts that students sort of applied was between whether or not they were sort of school-level concepts, that is, concepts that they'd learned before arriving with us to university, or concepts that we introduced in our sort of first-year course. And so that's highlighted in sort of green and in blue if they're sort of a school-level concept or a university concept, respectively. And so with correct students, what we found is they're engaging with all the school level concepts, but also are engaging with the university level concept of resonance that's introduced in our first year course. And so they're using the university level concepts to understand how the carbonyl group reacts, and they're using polarization of the carbonyl bond to understand why nucleophiles react at carbon. They could have used FMO theory as well for that understanding of the carbonyl reactivity, but across all the questions we never saw students sort of engaging with FMO theory. It was always polarization instead. And also students were engaging with the university level concept of resonance as well. So they recognise that in the ester you have this lone pair of electrons that could feed in to the ester carbonyl group, making it less reactive, hence the reaction occurs at the ketone. With partially correct students, what we found is that in their responses, they got the reactivity of the carbonyl correct again, so they recognised that nucleophiles react at the carbon, but this time they thought that the ester was the more reactive carbonyl functional group, so they had the ester reacting like so. And so if we think about their concepts that the students were applying, what we saw again was that students got the concepts of the carbonyl reactivity correct, and again they're using electronegativity to understand why the carbonyl reacts carbon. However, students were also engaging with electronegativity to understand why the ester group was more reactive, and so what they're doing is they're seeing this group here as being electron withdrawing, and hence making this carbonyl group more polarized and more electrophilic, and not engaging with sort of the university concept or resonance to understand why actually this lone pair can feed in to make that carbonyl less reactive. And we saw that with partially correct responses of other questions as well, where students were engaging correctly with the school level concepts, but they weren't engaging with the university level concepts, which was needed to give the fully correct answer. So hence their answers were always tended to be partially correct. And then finally we have sort of incorrect responses. And then so for carbonyl chemistry, we found that students were given responses where they were polarizing the bond to seeing this oxygen as being sort of delta negative, but that meant that they thought that the oxygen was nucleophilic, and so hence reacting with a species like borohydride as an electrophile. We also had another question involving a Grignard reagent, and again the incorrect students for that question also thought that the carbonyl group reacts to oxygen rather than carbon as well. And if we think about the concepts that the students were using, again, they're engaging with the school level concepts. So as I mentioned, they're using polarization to try and rationalize and understand the reactivity of the carbonyl group, but they're doing so incorrectly. So they're incorrectly thinking that it reacts with the oxygen rather than at carbon. So as I mentioned before, the main fault line between the students' responses was whether or not this concepts were school level concepts that had been taught before arriving to university, or the ones that we introduced in our sort of first year course as well. So with all the questions, we found that generally correct students were able to apply both school and university level concepts quite well, but partially correct students were only engaging with the school level concepts, not using the university level concepts. However, they were using the university level, school level concepts correctly. And then finally, the incorrect students were always only engaging with the school level concepts as well, but they were doing so incorrectly. So from all of our results, from all the diagnostic test questions, this has led us to sort of think whether or not these university level concepts are in fact kind of threshold concepts or difficult concepts for students to kind of get their head around. And what we found from our results is that we think that actually what's connected to their understanding of these university level concepts, school level concepts, is sorry, let me start that again. What we think is connected with the understanding of university level concepts is whether or not students' sort of use of school level concepts is hindering their understanding. So if I talk through the example of the question that I've given so far, talk through in more detail, I've explained how students are relying on electronegativity and polarization to understand how a carbonyl group and functional groups like esters react. And that's fine in the sense if students get the answer correct, so they understand if it reacts at carbon. But we've also seen the misconception of how this polarization could lead to some students thinking that the carbonyl group reacts with electrophiles at oxygen. And again, that sort of shows up a flaw in the simplicity of the model of electronegativity, and where a concept like FMO theory, for example, would help students actually understand the difference between the two. We've also seen the answers where students are using polarization to incorrectly understand the reactivity of different functional groups like sort of esters and ketones, where they need to also engage with concepts at university level like resonance. And so what we thought was actually what we need to do is get students to understand how the models like electronegativity are only simple models. They have limitations, and hence if we can get them to see the limitations of those simpler models, then maybe they'll be able to understand these kind of higher order concepts like FMO theory and resonance. And maybe the reason why they're struggling to understand or use or apply those concepts is because they don't see what's wrong with only using concepts like electronegativity. Okay, and so yeah, it's just whether or not seeing if students are happy with the simpler models, and that's hindering their progress with those higher level concepts, which in turn are making them threshold concepts. And so we looked at applying this into our teaching of carbonyl chemistry at Leeds. And so this is delivered in a lecture course by Paul Taylor. And so we're very grateful for Paul for being interested in our results and being very keen to see if we can apply our research into improving how students understand those concepts like FMO theory and resonance. And so we've been looking at using sort of active learning approaches, so using some of his lectures and workshops to generate, design sort of workshops that we can use where we can get students to understand concepts like resonance. And our approach has been to use a framework of teaching and getting students to sort of change their old ways of thinking and adopt new ways of thinking called the conceptual change framework, which was first developed by David Tregust. And this involves sort of three approaches and three sort of steps, and we use these three steps in the design of these sort of workshops. So the first step is getting students to become dissatisfied with their old ways of thinking. So knowing that students sort of rely on electronegativity as their sort of favoured model of understanding structure and reactivity, what we wanted to do was first engage students in some guided activities that show the limitations of electronegativity and show how it fails as a particular concept. So getting students to understand the concept of resonance, for example, we first get the students to work through activities where we get them to think and predict what the reactivity of different carbonyl functional groups would be, only using the concepts of electronegativity. And then what we do is we actually show that up and show that actually that doesn't fully reflect what the actual reactivity of these carbonyl functional groups are, showing up the limitations. And then what we do is then we introduce the concepts of resonance and how this particular concept also applies to sort of carbonyl functional groups. And then we finally, through the sort of final guided activities in these workshops, sort of show how resonance will sort of give you the correct answer and give you the correct sort of order of reactivity as well. So that kind of structured approach we've used to try and get students to understand resonance, but also another threshold concept that we think we've identified, FMO theory as well, to show why sort of nucleophiles react at carbon rather than oxygen instead. So that's just an example of some of the research that we're doing, trying to find out how students sort of conceptualize organic chemistry and then turn that into improving our teaching practice. And so what I'd like to do is thank a number of people who've also been involved in this project, and I can't thank the students that I've worked with on this project enough. Stephen is a project student who's helped me sort of analyse the diagnostic test questions and interpret the findings. Michael is a student who has helped sort of design the workshop activities, and he worked with myself and Paul Taylor to come up with the correct sort of activities that we implemented. Paul, I mentioned before, who teaches carbonyl chemistry, again, has been really sort of helpful in sort of interpreting our results and implementing those workshops. I'd really like to thank Samantha Few, who through PRISM has helped us gain sort of ethical approval for this work. We've also had good support from the head of school, Steve Marsden, who has also actually helped to fund some of the project students' work towards this work that I mentioned today. And then also Rafe Hallett, who's director of the Leeds Institute for Teaching Excellence, and so he funded my work on this project and some time for me to spend away from teaching just to fully investigate this work that I presented. And then finally Russ Kitson as well, who's a teaching fellow at Warwick, who has helped run those quizzes and gave the responses that we've seen from Warwick students as well. And then finally, to thank you guys as well for listening to some of the work. And if you have any questions that you'd like to ask, then feel free to contact me via email or through Twitter as well. Thank you.